This video covers how to use L'Hopital's rule. And yes, it looks like it's spelled La Hospital, but please do not pronounce it that way. So first of all, we can only use this rule whenever we're working with a limit that gives us indeterminate form. And remember, this happens when the result is 0 over 0, or when we get our infinities over infinities. So you cannot apply this rule for other limits that do have a determinate form, and in your work you must show that you have checked to see that you get either 0 over 0 or infinity over infinity before you can apply it. Okay, so if that is the case, then the rule states that we have two functions, f and g. So suppose f and g are different. Functions. And that g of x does not equal 0 near some value a, but that is a keyword, near a. It might actually equal 0 at a exactly, which we'll get to in a second. So except, I know this sounds confusing, except maybe at a, and the limit as x approaches a of f of x equals 0, and the limit as x approaches a of g of x equals 0, or the same thing but with infinities. So kind of like what we just talked about, where you have to kind of show that this is the case, that you're getting indeterminate form. Okay, and those could also be negative infinities as well. If all that is true, how does this have anything to do with derivatives? Well, that's what the rule is going to tell us. Then the limit as x approaches a of f of x divided by g of x, here's the fun part, equals the limit as x approaches a of f prime of x over g prime of x. So this might seem kind of out of place because it's been a while since we've talked about, we still talk about limits, but that unit was a while ago, but we couldn't do L'Hopital's rule in the unit on limits because we have just now gotten to where we know how to take derivatives of all the types of functions we work with. So basically, if you can show that it's indeterminate form, then you can apply this rule that actually was not invented by someone named L'Hopital. Fun fact, it was actually Johann Bernoulli who discovered L'Hopital's rule in the 17th century, but it was published in a book, actually the first ever textbook on differential calculus, by a man named L'Hopital, so he kind of got credit for it, but we know it was really Bernoulli. Okay, so before we start the new stuff, let's try to remember what we did do with these problems back in the first unit before we knew L'Hopital's rule. So it's been a while. And remember, the first thing we tried with limits was direct substitution each time. So for this particular limit, if I did direct substitution, 2 times negative 1 squared minus 2 over negative 1 plus 1, and we can obviously see the denominator is going to be 0, but we want to make sure the numerator is also 0 so that we can show its indeterminate form, and this of course will become a positive 2 minus 2, and so it is. And remember, if this were the case, where we had 0 over 0, this was our sign that there was some sort of whole we could simplify. And so with these, we often did some sort of factoring. So let's do that real quick. On the top, I can factor out a 2, get x squared minus 1, which of course factors. Let's see. Into x plus 1. And x minus 1 over that x plus 1. Okay, and then we were able to cancel out those factors And we were left with the limit as x approaches -1 of 2 times x minus 1, which if we substitute in would give us 2 times -2, which is -4. Okay, so this is how we did this particular problem prior to L'Hopital's rule. Okay, so how do we do it with L'Hopital's rule? Well, if we look back at the definition, they've gotten a lot more strict about this on the AP test. They want you to actually write out the limit as x approaches a of f of x equals blah, and same for g of x, before you actually apply the rule. So like it used to be all you had to do was this, and then you would just do it and then do it again, but now they actually want you to write it out, so let's practice that. So first let's do it for the numerator, 2x squared minus 2. We already know if you plug a -1 in, we're going to get a 0, and then we're going to do it for the denominator function, g of x, and again if we plug in a -1 we get a 0. So this tells me to use, I don't know if I can fit this, L'Hopital's. Okay, so that's how I know, let's make this look a little bit less crazy. That's how I know I'm going to use L'Hopital's rule. It's because I found these limits at the top and the bottom, and they create 0 over 0 in this case. So now we're going to actually find the derivative. So our new function is the limit as x approaches -1. We're going to take the derivative of the top, so this would become a 4x to the first. The -2 will go away. Over. And down here, we're just going to be left with a 1, and the +1 goes away. And then that's really just the limit as x approaches -1 of 4x. So I definitely know I can do direct substitution now because I no longer have a denominator. So that's just going to be 4 times -1, which is, of course, what we got on the previous slide, a -4. But you can see on this particular example that it's a much faster option for us to just take the derivative of the top and bottom, and then we're able to do direct substitution much faster. Okay, so again, way back at the beginning, let's see what we would have done on a problem like this. So this is one where x is going to infinity. With these, we use the end behavior model and Nefepel, our good old friend Nefepel. But if you tried to do direct substitution here, you would get a really big number squared over a really big number squared. So this is the kind where we would have gotten some sort of infinity. The question is just, is it plus or minus infinity? We weren't sure. But in the sense of indeterminate form, right, we would get infinity over infinity. And so that was a problem for us. So what we did back at the beginning of the unit is we used the end behavior model, which stated basically that we can just focus on the leading terms of the highest powers and compare to see which one was dominant on the top or the bottom. So for this one, it's a polynomial. These aren't so bad. We would have focused solely on 3x squared and 2x squared. Okay, because the -1 and +1 really doesn't make a huge impact when we're talking about infinitely large numbers. And then if we had worked with those, the x squareds would have simply canceled out, and we would have gotten a limit of 3 over 2. So for our answer, we simply would have written the limit as x approaches infinity of 3x squared minus 1 over 2x squared plus 1 is simply 3 over 2. Okay, so this one wasn't so bad. It was just kind of not the most concrete thing for some of us, so we still struggled a bit with that. So now let's try it with L'Hopital's rule. Okay, so we're going to find the limit of the top and bottom separately. Okay, and so for 3x squared minus 1, we know, first of all, we're going to positive infinity, but we're squaring it as well, so it's definitely going to give us a positive infinity. And then the same for the denominator, 2x squared plus 1 also gives us positive infinity. So that's telling me to use, I'm just going to abbreviate L'Hopital, but you should write the whole thing out on a test, obviously. We know we're going to use this rule because we're getting indeterminate form of infinity for the top and the bottom of the fraction. Okay, so let's take the derivative of the top. we're going to get 6x to the first. This guy goes away. And on the bottom, we're going to get 4x to the first. That one goes away as well. Okay, so we're not done here because there's still variables to plug infinity in for. So we would run our test again. So the limit as x goes to infinity of 6x. Okay, that's just going to be a big positive number. And then same for the denominator. And again, we're getting infinity. So still indeterminate form. So I need to use L'Hopital's rule again. So basically, we just continue this pattern as many times as we need to until we get something that's not indeterminate form. So the derivative of 6x is 6. The derivative of 4x is 4. And obviously, that's just going to simplify to 3 over 2. Okay? So that's how we can get the same answer as we did at the beginning of the unit, but without having to remember the end behavior models or NFEPL. All right. So this was another common type of problem we ran into with limits where when we do direct substitution, let's see, that would be 7 plus 2 minus 3 over 7 minus 7. And this would just be square root 9, which is 3 minus 3. So again, getting 0 over 0. And if you remember, what we had to do with these is rationalize. So we would keep the original problem, and then wherever we had that radical, we would multiply by its conjugate on the top and bottom. So the conjugate in this case would be square root x plus 2 plus 3 to get rid of that, right? And then here we would get the limit as x approaches 7 of, this is really going to give me whatever's under the radical squared, which just leaves me with what's under the radical. So x plus 2, and then a minus 3 times a plus 3 would give me a minus 9. Then our denominator would kind of be ugly, but usually something would cancel out for us, so we definitely would not distribute anything. And if we clean this up, we see that x plus 2 minus 7 can just be written as x minus 7, which nicely cancels out with what's in the denominator. Okay, and so we ended up with that getting canceled. And that's good because our big issue was the 0 in the denominator with the x minus 7, which will no longer be a problem. Okay, so now we can actually do direct substitution. That was way too long of a divide sign. Okay, so we would get 1 over square root of 7 plus 2 plus 3, which equals 1 over 3 plus 3, which equals 1 over 6. Okay, so that's how we dealt with these radical problems previously. Now let's try it with L'Hopital's. Okay, so we know we need to check the limit, and from our previous work on here, we can kind of just know that the square root of x plus 2 minus 3, if I plug in a 7, that's going to give us a 0, and obviously with x minus 7 we get a 0. So we're still going to use L'Hopital's rule, but you do need to write it all out again, like I said. I just can't fit it on this particular screen. Alright, so this might be a little ugly. We got to take the derivative of this. So let's just remember that that's really going to be written as, let's see, x plus 2 to the 1/2. I'm just going to rewrite it first before we actually take the derivative. Okay, so then that can be written as, take the derivative, that would give me 1/2 times x plus 2 to the negative 1/2. If we derive minus 3, it goes away. This leaves us with a 1, and that goes away. So we might not have to do it again if we just clean it up. A lot of times you don't have to take the derivative more than once. So let's see. We're just going to pretend this denominator's gone. So we're left with a fraction. We know we have a 2 on the bottom, and since this is a negative exponent, we know that's also going to go in the denominator. All right, and we should be able to do direct substitution now. All right, 7 plus 2, which just gives us 2 root 9, which gives us 2 times 3, and guess what that gives us? The answer we already knew, 1 over 6. All right, for our last example, this is one we would have probably used nafethyl on. Remember, it was like the function that is a variable to itself, factorials, exponential, polynomial, linear, which are really types of polynomials, and then logarithmic. This told us who would win in decreasing order. So if you're looking at this one, we have an exponential over a polynomial, and so the exponential would be the more dominant ones, and so this one would have just gone to a positive infinity since it was in the numerator, and that would have been all we really could have done for that using our old methods. But now we're going to try it using L'Hopital's rule. So the limit as x goes to infinity of e to the x is just going to be e to a really big number, which is just a really big number. And the limit as x goes to infinity of x squared is a really big number squared, which is still a really big number. So we'll use L'Hopital's rule here. All right, so this is where our more recent derivative skills come into play. So the derivative of e to the x is itself, and there's no chain rule there because it's just an x. And the derivative of x squared is 2x. Okay, so let's see if we do the limit as x goes to infinity of e to the x, we're still going to get an infinity there. But for 2x, we're still getting an infinity, but you can probably see why it is that exponentials are always going to beat out polynomials using this method. Because each time I take yet another derivative of that numerator, it's not going to change because that is the special property of exponentials. However, this polynomial function keeps going down a degree and a degree and a degree, and now it is simply a constant, right? So we could even rewrite it at this point, the limit as x approaches infinity of 1/2 e to the x, and that sometimes makes it, gross, makes it easier to see that at this point this is going to be the determining or more dominant part of this problem, and since it is going to a positive infinity, the whole thing is going to positive infinity. So that concludes the lesson on L'Hopital's rule. I hope you're excited because it's really a nice shortcut when you get to some of those harder limit problems. And now we'll be able to do the Mean Girls problem, so get pumped for that. And this concludes our lesson on L'Hopital's rule.